Chapter 3 begins the modular approach to the remainder of this book. And Module 1 starts with the calendar. It's going to turn out that how we use the calendar in finance, the movement of money through time is central to almost every finance calculation, and hence the ability to compute, for example, the number of days between two dates, and how you count days is very important. And so the different contracts within finance will specify exactly how to count days, and we'll look at this in detail. Meticulously accounting for the day count and payment frequency is very important. The most common types of day counts are what's known as actual 365, where you count the actual number of days. For example, if I have a semi-annual coupon paying bond, if the coupons are computed based on actual over 365, then you simply calculate the number of actual days between two coupon payment dates. You divide that by 365, and you get the fraction of the year that will be used in different coupon amount calculations and other types of cash flows. Actual takes into account leap year effects. Another popular method of computing days that dates back to prior to having easy access to computers is what's known as 3360. And so there's an implicit assumption of 30 days in a month divided by 360. Another popular method, particularly used with money market instruments, is actual over 360. You calculate the number of actual days, say in a quarter, you divide that by 360. Typically, the way this is done is dates are converted to Julian numbers. The Julian method converts each day to an integer, and the difference between these integers gives you the correct day count. Unfortunately, different software packages assume different base years, such as Microsoft Excel. At least some versions of them assume the 0 day is December 31st, 1899. Different R packages will assume either January 1st, 1960 or January 1st, 1970. Clearly, if one date is computed based on a base year of January 1st, 1960, and the other date is based on January 1st, 1970, then I'm going to be off by a decade. The frequent mistake made with R coding is you import data from a spreadsheet. It's based on a December 31st, 1899 date, and then once you're in R, if you're calculating dates, you're going to be off by 60 or 70 years. So you have to pay attention to the base year. This is a recurring challenge for quantitative analysts, is making sure your Julian calculations are consistent across your entire platform. The code, just to give you an idea, we'll spend some time looking at this particular module's code, but the way this typically works, if I input, say, a start year and a day and month, and then input an end, month, day, and year, the Julian start date, I can convert month, day, year to a Julian number, and so the way this is stored, if I just print out Julian start date, it gives me a date. But if I convert it to integer, it shows me the integer value of 21,915. But the class, the type of variable that this is date. So it publishes as a date, but the number stored is integer. And then I have an end date, and it's integer. And so we can say something like, give me the number of days between this Julian end date and this Julian start date. Days is in fact an integer, and so the start date and end date in the days, the dates are actually printed out in day, month, year format, but the number of days between two dates, this is about 30 years, which is about 11,000 observations as we would expect. And so an alternative is I could go ahead and convert these date variables into integers themselves, take the subtraction, and then the outputs are all three of them are expressed as an integer. And so this is a way to go from a Julian stored date to the number of days. Alternatively, it may be that we have a Julian number and we want to convert it to a start date. And so when we do that, we'll use the function date.mdy, and this basically returns a vector. And so in summary, we explored the means to manipulate the calendar dates, which is highly useful in finance. We reviewed date types and Julian methods. We're fixing to explore some selected R code. Again, we're going to begin taking a modular approach for the remainder of this book. And in Chapter 3, there are 7 modules that we will cover. We're focused at the moment on the calendar module. And so you will find a zip file with all of these programs. But at the moment, we're just focused on the calendar module. So once you unzip it, you should be able to go into 3.1 calendar. And then if you click on the RPROJ file, it will launch R, and R will open however it was left. If you'll notice, I left this cleaned out, and so there's no residual plots or environment variables that I need to concern myself with. Again, you can just run the entire code if you wish and see what all it does. You can check out the files. If you'll notice, there's 3 different test files. One is an ancient calendar test. I was playing around with counting the number of dates from the ancient calendar just for fun, trying to figure out how the base year, 0 year, is handled in a variety of different calculations. The role that compounding frequency and day counting play is explored in this particular test routine. And so, but at the moment, we're just looking at a simple calendar test program. And so running this program, if you just run it line by line, that just cleans out the variables. If you'll notice, there's the rquantlib package, there's date, there's TIS, and there's JRV finance. And so the rquant library is useful for many built-in packages. The date calendar is a package that's been around for a long time. If I run these lines, those particular packages will be attached to this particular project. And so again, looking at the Julian start date of, say, June 1st, 2019, if you'll notice when I run these 4 lines of code, it produces 3 integer variables and 1 date variable. The Julian start date, if you'll notice, it's reported here as 21,701. And then if I do the same thing for 1 year later, this is 22,067. And so I could convert or I could move these variables over to, say, date 1 and date 2 if I wanted to, and I could do a simple subtraction and get the number of calendar days. And so what we observe is that 2020 is in fact a leap year, so there's 366 days in that year. The many libraries provide for you calculations of different day counts, and you have to go to like rquantlib and figure out this year fraction gives you different calculations. And so F1 in this particular case is a little greater than a year because it's actual over 360, and there's actually 366 days. And so just to test that out, you'll notice these two give the same number. And then we could look at actual over 365. Again, they give the same number. If we use 365 actual over actual, that is 1.002, and then we get the same result here. And so depending on if we're interested in business days, and there's a whole host of other calculations I don't want to spend the time to go through. Depending on the context of your project, you need to know what the legal requirements are for different calculations. Typically, this is not a logical issue. This is a legal issue. And there's certain securities industry standards, and there are books published by different associations that provide these standards. And so these various different calculations are based on legal methods more than they are logical methods. There was an old package, JRV Finance, that worked for a while, then didn't work for a while, and now works. And so it's always good to have a variety of different ways to do these calculations. Packages, unfortunately, in R are not stable. If the creators of these packages change their mind on something, then in fact the way these packages behave changes. And so the beauty of R and RStudio is that it's free. The unfortunate disadvantage is that it is not permanent. It's not that stable, particularly if you rely on additional packages. So one common thing that people want to do is pull the date that's currently on your computer. And so sysdate is the way to do that. And again, if you just do the question mark with single quotes, you get the system time and date. How you manipulate this, today's date, this is stored in of 8, and the day I happen to be doing this video is August 28, 2023. I can extract from that the today's date, month, and year. And so it's August 28th, 2023. I could convert that to a Julian date if I wish. And that's 23,255. And then I could just print those out to check, see if that makes sense. If I take if I take today's date, and then I just pull randomly some date in the past, that is, say, significant for me, that I can compute the actual number of days since that date, 13,589 days. I could convert that in fractions of a year, and that basically tells me that my 38th anniversary is coming up in the future. And so you can just check various dates to see if, in fact, you can go back and forth between the Julian number and a month, day, and year. I could do the same with the end date and be able to go back and forth between being able to have the month, day, and year and have the Julian number. And so there's a host of different issues that come up in finance. One of them is holidays and weekends and that sort of thing. And so if I pull January 1st of 2022, it is a holiday. And so if X, in this case, a particular Julian number, if I set Presidential Inauguration Day is not a holiday, I can compute the next business day is January 4th, and then the previous business day is December 31st, and you can begin to see there's a whole host of different things that you can do. I don't want to take the time to go through that. The final thing I will say on this particular package is you can build your own date counting function, which is what is done in this particular package. Is given a date, I can adjust that date to modified business preceding or modified business following. I recommend that you spend some time with this code to get increasingly familiar with all the things you can do with R programming.